Hi everyone, and welcome to another Making Physics Easy webinar. So today's topic is MR imaging, and we'll be covering the topics that are for radiologists who are sitting FRCR Part 1 Physics. So the point of the Making Physics Easy series is so that people who are sitting their Part 1 Physics exam can get the help that they need with their physics preparation. So we explain the curriculum in detail. We provide you with MCQs. We're developing something soon on the platform where you'll have your own revised radiology MCQ system. And we're also available on the FRCR Part 1 group, which hopefully you're a part of, and the chat as well for you to ask any questions that you have regarding the content that we cover. So that's a little introduction to the Making Physics Easy series. The way you're supposed to use the series is along with your other preparation. So while you're reading your textbook or preparing from your MCQ books, if you could also attend these webinars and listen to these lectures, that would be a really good way of preparing for your exam. So let me just, So let me introduce myself before I start teaching. My name is Joanna Koshy, and I have an MSc in nanoscience. So I've created this Making Physics Easy course along with Dr. Koshy Jacob. So we've spoken to lots and lots of consultants and lots of trainees about their physics examination, what was easy, what was difficult. We've referred to a lot of textbooks, and it's on the basis of that we made this physics course. So today we're going to be discussing MRI, which is a particularly difficult topic for most people. So the lecture will continue for around 45 minutes, and then we'll have time to ask questions for another 5 to 10 minutes. So let me get started. We'll be discussing the fundamentals of MRI, including, first of all, what are the advantages? So magnetic resonance imaging is non-invasive, non-destructive, and non-ionizing. The advantages of MRI are that it has superior soft tissue contrast when compared to CT and X-ray. That's because in CT and X-ray, it's the parameter on which the contrast is created is the linear attenuation coefficient, which basically depends on the density of the material. Whereas in MRI, the parameter on which the contrast is created depends on its relaxation periods. And that depends on the number of protons in the material. So it's a completely different type of, and we'll go into this in detail during the course of the lecture, but it's a completely different type of parameter on which to base things. And with the parameters in MRI, we are able to see soft tissue with better contrast than in CT and X-ray. More advantages of MRI, you can get multiple plane imaging without repositioning the patient. You get precise tissue characterization and advanced visualization. So what are the clinical parameters that we're able to image with MRI? So there's T1, there's T2, there's proton density, there's T2 star, blood flow in arteries and veins, perfusion of blood through organs, molecular diffusion of water and tissue, blood oxygenation, and numerous metabolites. So these various clinical parameters we're able to image through MRI, which means that it's a imaging modality which has a lot of variety and scope. You can image based on a lot of different types of parameters and generate a bunch of different types of images. So what are the disadvantages of MRI? For one thing, it takes longer, which means that especially for kids, the patient might not be able to sit still. It has contraindications in case there's metal present in the patient's body. It's costly. Motion artifacts can occur because it takes a long time. It's noisy. For patients with claustrophobia, it might be difficult to deal with. It's especially difficult to understand for radiologists. They have a tough time understanding the physics of MRI because the theory involves, quantum mechanics and things like that. And in some cases, CT is a better choice, but that's true of any imaging modality. In some cases, it works better than in some other cases. So let's move on to the physics of how MRI works. So first, we're discussing what exactly is happening. So the basic physics of MRI says that a magnetic field is applied and then the atomic nuclei are manipulated, which causes a signal to be produced, which then turns into an image. So there's a magnetic field which is applied to the patient. This magnetic field is going to interact with the atoms in the patient's body in a certain way. And yeah, so sorry about that. I'm getting a lot of notifications. I'm not sure how to switch off the sound of that without it bothering everybody. That's my Telegram desktop notification going off. Please ignore that. Hopefully it won't continue. Yeah, so the magnetic field is applied and then the atomic nuclei are going to interact with this field. They're going to produce a signal. We'll measure the signal and then we'll translate that signal into an image that you, the radiologist, will look at and interpret, clinical things from. So the basis of this imaging modality is a phenomenon which is known as nuclear magnetic resonance. So how do we understand nuclear magnetic resonance? That's what we're going to be looking at in the next section. I'll go through these concepts many, many times. And if you have any questions at all, put them in the chat box, because this webinar is the beginning of a series of webinars on MRI. And the concepts that we're discussing in this webinar are really crucial for understanding the concepts in the later webinars. So I'm going to take my time and I'm going to explain everything here very thoroughly and in detail so that you're able to apply these concepts in the later webinars and fully understand the imaging modality that is MRI. So first, we're going to look at this thing called nuclear magnetic resonance, and we'll break that down and see what that's about. So let's start from the very basics. Let's start from what is a proton. So the hydrogen nucleus has a single proton inside it. A proton is a subatomic particle. It's got mass, it's got a positive charge, and it's got something called spin. So just the way that the Earth spins on its own axis, protons have spin as well. And because it's a charged particle that is spinning, it acts like a tiny little magnet. And protons are present in all over the body, including in bodily fluids, water-based tissues, and fat-based tissues. So wherever these protons are present, the MRI, the magnetic field is going to interact with them. So the basic actor in this play is the proton. And the proton is exactly what we've described right now. And we talk about hydrogen nuclei as basically being protons. Now, why is it that we don't talk about other types of atoms? Okay, so nuclei with an even number of protons, like 2, 4, 6, 8, don't behave like magnets. And nuclei with odd protons, besides hydrogen, are few in number in the body. Why are there a lot of hydrogen protons in the body? Because there's a lot of water in the body. So because of this reason, the nuclei with odd protons have a weak signal, for example, phosphorus. Yeah, you might ask at this point, what about the electrons in the body? Don't they contribute to MRI at all? The answer is no, and I'll explain why a little later once we discuss what a radio frequency signal is and how it's related. So it has something to do with the way that the proton and the electron spin differently. I'll come to that in just a bit. So these are the basics. This is the basic actor in the play of the MRI. And if you have any questions at this point, you can put them in the chat. Otherwise, I'll keep going. So a little theoretical point to discuss before we start going. If anybody remembers their electromagnetics, you might remember that there are there's H and then there's M. So M and there's B. So B is the field that we're applying to the patient. M is the magnetization, mu is the magnetic permeability, and H is the magnetic field in the patient. So we're talking about the magnetic field applied to the patient. We're talking about how the atomic nuclei react, but all the while we'll be using the term B instead of H. So if you know your electromagnetics, you'll be asking, why is it that we're talking about B when we really mean H? So the reason is because we know that there's this formula that exists, which is the field in the patient is related to the field, external field, which is applied, but there's these other factors in the equation like mu and M. So you might be asking, what happens to mu? What happens to m? Why are we talking about d instead of h? So the fact is that mu is close to m for the human body, and the magnetization is incredibly small compared to the external field that's applied. So therefore, B and H are nearly identical. And for this reason, when we're talking about the magnetic field that exists in the patient's body, we're going to be using the term B instead of the term H. So this is really for, if you remember your electromagnetics and you remember that formula that exists, if you had a doubt as to whether the magnetic field, external magnetic field that we apply to the patient is the same as the magnetic field that exists within the patient's body, the answer is yes. The two fields are nearly identical, and so we speak of the B in all the future slides that we'll be going through. Here, B is the external magnetic field that's being applied. So continuing to go through the basics, we're now discussing the spin of the protons. So there's a formula over here, which is L is equal to IH by 2 pi. So the spin is measured by a vector quantity, which is the angular momentum L. L tells us how much the proton is spinning and in what direction. And it has values given by the formula that I put on the screen. Now, I here is a quantum, that's small letter L. Quantum number L can either be 0, whole numbers, or multiples of 1 by 2. The magnetic dipole moment. Magnetic dipole moment is mu. Mu tells us how quickly a magnet aligns with a magnetic field. Gamma is the gyromagnetic ratio. Gamma depends on the type of nucleus. So we're just covering some basics here. We talked about the proton already. We said the proton is spinning. Now, there's something called the Larmor frequency, for which we have to introduce a few other terms. So first, we have to describe how the proton is spinning. So the way that we describe it is we use this term called L, which describes the spin of the proton. It's basically, the spin of the proton can either be 0, or it can be h by 2 pi, or 2h by 2 pi, or half h by 2 pi. H here is a constant, which is known as Planck's constant. So basically, it's a number, and it's either, you can think of it as a ball. So it can either be 1, it can either be 0, it can be 1 ball, it can be 2 balls, it can be half a ball, or 3 by 2 of a ball, but it can only have certain specific numbers attached to it. So that's how we'll think about the spin. We also will think about the magnetic dipole moment. So a magnet has something which is known as a dipole moment. And essentially what this dipole moment is going to tell us is how quickly the magnet will align with an external magnetic field. So you all know that if a magnetic field is applied, a magnet has a north and a south, and the north will align with the south, and the south will align with the north. So that's how magnets align in a magnetic field. Similarly, we discussed how the proton, which is a charged particle in spins, behaves like a tiny little magnet. So we're going to be thinking about what happens when we apply a magnetic field to the proton. What happens to the proton? So one of the things that we need to keep in mind is the magnetic dipole moment, which will let us know how quickly the proton will align itself with the externally applied magnetic field. So it's literally going to move its angular momentum in order to align with the external magnetic field. Okay, so those were some basic terms that we needed to introduce. If anybody has any questions about these terms, then you can bring them up now. Otherwise, we'll start talking about how all these various terms interact with each other in order to form MRI images. So we went through what is a proton. We went through why protons are important and not other types of atomic nuclei. We discussed why we speak of D instead of H. We talked about the spin, and we talked about the magnetic dipole moment. And these are all the ingredients of what we're going to be looking at in the next few slides. So if anybody has any questions, you can put them in the chat. Or if you're ready to keep going, you can put a yes in the chat box. And I'll take that as a sign that I can keep going. So I'll just wait for a few yeses to make sure that this part is clear. And then I'll continue with the webinar. Okay, so I've got a few yeses in the chat box. So let's keep going then. So let's look at, now we've been looking at things at a very atomic level. Now let's take the microscope and turn it into a telescope and look at what's at the macro level. So the setup here involves a bunch of magnetic fields essentially. So we have the main magnet, which exerts the external constant field on the body. It's a superconducting helium-cooled magnet, which ensures that the field remains as uniform and constant as possible. Then we also have radio frequency coils, which are capable of both transmitting and receiving radio frequency signals. We also have magnetic field gradients, which are gradients that are applied in 3 different directions and which help us localize the MRI signal. Now, all these things are controlled by the computer system, except the main magnet. So the RF coils and the gradient coils are controlled by the computer system. So that's the basic setup of the MRI. Now let's see how this setup produces the image that we're talking about. So as I was saying, the main magnet produces a strong static field B naught. The RF coils excite protons by producing a radio frequency signal. They also receive the radio frequency signal, which is then emitted by those protons. Magnetic field gradients localize the signal, as I said, and the computer system converts the signal to image, participates in archiving, etc. So what happens? The patient is put in the field B naught, which is exerted by the main magnet. So this field B naught can have values of either 1.5 Tesla or 3 Tesla. And you should know that this is a very, very strong magnetic field, several times greater than the magnetic field of the Earth. So the patient is put into this magnetic field, which is created by the main magnet. And all the protons in the patient's body, which are tiny little magnets, will have a reaction in response to this magnetic field. So they will either align with the magnetic field or they will align against the magnetic field. And you should know that more protons align with the field than against the field. And we'll discuss why in just a second. So you might be confused at this point because if you've ever played with magnets in your life, you'll know that in the presence of another magnet, they only ever align in the same direction. So why is it that these magnets can either align in one direction or the opposite direction? And the reason for that is that the magnets we're talking about here are quantum magnets. So we have to expect them to behave in ways that are different from classical magnets. That's kind of a hand-wavy explanation, but we'll talk about what it means for magnets to align in 2 different directions in just a second. But the answer is that it's a quantum magnet and there are quantum effects at play, which cause the alignment of the field to be one or the other. Okay, so if you take a look at the diagram on the left-hand side, you'll see there's a magnet, which is a proton, which is aligned a certain way, and a proton, which is aligned in the opposite way. And when the magnetic field is applied, basically one set of protons aligns with the field where they have lower energy, and another set of protons aligns against the field, and then they have a higher amount of energy, which makes sense, right? Because imagine if you're in a river, and the current is flowing very strongly. It's easier for you to flow along with the current, whereas if you're going against the current, you need a greater amount of energy. So in the same way, the protons which are aligning with the field have a lower amount of energy, and the protons which are aligning against the field have a higher amount of energy. Now, this amount of energy is given by the formula h mu, where h is Planck's constant, which we saw again earlier, and mu is the frequency. And it has a certain number, which is related to the magnetic field we've applied, directly proportional to the magnetic field that we've applied. So if the direction of the magnetic field changes, a different alignment occurs. Now, so what we've done is we've applied a certain magnetic field and the protons have aligned themselves in a certain way. Some have higher energy, some have lower energy. Now what we do is we flip the direction of the field. What's going to happen is the protons align in a different way. A whole bunch of protons will flip, a whole bunch of protons will, yeah. So what happens then is that the energy of the protons is changing. Some protons lose energy and some gain energy when the alignment changes. So now if the magnetic field starts to oscillate, by oscillate we mean, so sorry, that's my Telegram chat again. Let me just open that up. Yeah, okay. So what we mean by oscillate is that the magnetic field is applied in one direction, which means the north to south is in a certain direction. Then suddenly it's flipped. The south is in the opposite direction and the north is in the other direction. And by oscillate, we mean that it starts going up and down really rapidly at a certain frequency. So when that happens, the protons also start changing from the high to the low energy state quite frequently. Now, this frequency at which they start changing to a different magnetic state is given by the formula above. And this oscillating magnetic field is equivalent to an electromagnetic radiation of similar frequency. So oscillating magnetic field is equivalent to an electromagnetic radiation of similar frequency. So what happens is there are more low energy protons. That's a given in any natural system. There's always things which are at a lower energy compared to things which are at a higher energy. So when the field oscillates, there's a net gain in energy that happens. So because the lower energy is going to the higher energy, so there's more higher energy protons later, which means that the system as a whole has more energy. So this gain in energy is from the absorption of the radiation energy. So this energy will later be radiated as a signal. And when B naught is 1 Tesla, the frequency mu of the radiation that's emitted is 42.6 megahertz, which is in the radio frequency region. So let me just try to explain this. We've had a lot of formulas. We've had a lot of numbers thrown in. So let's just try to discuss what happens. Essentially, if the magnetic field starts to oscillate at a certain energy, the protons can change from the high to the low energy state, and there's a net gain in energy. That frequency of oscillation is given by the formula that I've written on the top. Now, yeah. And the interesting thing is this frequency of oscillation can be used, an oscillating magnetic field can also be used, you can apply an electromagnetic radiation with the same frequency, and they're both equivalent to each other. So which electromagnetic radiation are we applying here? It's the radio frequency. And you can see here that when the external field that is applied is 1 Tesla, the frequency mu will have the value 42.6 megahertz, which is in the radio frequency region. So this is all to answer the question, why are we applying radio frequency to the protons and not some other kind of frequency? The answer is we need to make the protons oscillate up and down in their low and high energy state. And in order to do that, because the value of the external magnetic field is around 1 Tesla, 1.5 Tesla, 3 Tesla, the oscillating magnetic field that we need to apply will come from an electromagnetic radiation in the radio frequency range. I hope everyone's familiar with the electromagnetic spectrum, but yeah. So eventually what happens is this oscillation causes the protons to go to a high energy state. Once the oscillation of the magnetic field stops, the protons will lose the energy they gained or relax. So this relaxation gives us useful clinical information. So that's essentially what happens, and we'll go through this in detail and find out what happens. So we were discussing why do some protons align against the field, because that doesn't happen in classical magnets. So let's discuss why that happens in terms of proton alignment. So a normal magnet would lie exactly along the field. A normal magnet is the one I put on the left-hand side. The protons are ruled by quantum mechanics. They all align at an angle to the field. Okay. So we've gone through a lot of concepts right now, and we're halfway through the webinar. If there's any questions at this point, you can discuss those with me. If not, I'm going to take a 5-minute break, just so we have time to go through our notes and see, are there any specific questions that you want to ask at this point? Any doubts that you have? Yeah, we'll just take a 5-minute break, and then after that, we'll go straight into the rest of the theory.